In today's video lecture, we're going to do a bit of review on congruence and similarity. So here's Ant-Man, of course, played by Paul Rudd, and you'll notice that he can be moved around. So if I select Ant-Man here, and I move him around, you'll notice that he's still the same guy. He's still the same height. He's still the same width. If he was a three-dimensional object, he'd still have the same weight. Moving him around doesn't change anything about his size or his shape. And in fact, I could go ahead and grab this corner here and rotate him around. And again, he still has the same shape, he still has the same size, and I think we can all see that sort of intuitively. Even if I was to go into Edit, Transform, and like flip him so he's now reflected, he'd be left-handed now, but he's still the same shape, he's still the same size, he's still really the same everything. So what we're seeing is the definition of congruence. Congruence means that two shapes have the exact same shape, the exact same size, the exact same everything. In fact, you could take one Ant-Man and put it directly on top of the other, and it could perfectly overlap just using those three transformations I just mentioned: rotation, translation, and reflection. But that's not what Ant-Man does. Ant-Man doesn't stay the same size. Ant-Man grows and shrinks. And this is the difference between congruence and similarity. When Ant-Man shrinks down, you'll notice that he still looks like the same person. He still looks like the same shape. Whether he's much larger or much smaller, he's still the same general person. You'd still recognize him as having a human shape, as being normal shaped, even if he's not normal sized. And the reason for that is proportions. Notice that when we grow and shrink Ant-Man, or at least this two-dimensional representation of Ant-Man, we are growing and shrinking the width and the height, the x and the y axes. We are shrinking them by the same amount every time. And when I say amount, I mean proportion. And when I say proportion, I mean multiplication. So if we cut Ant-Man's height in half, in other words, if we cut his height in half, we're also cutting his width in half. Now, there are a few ways that you can dilate things weirdly and distort them so that they are no longer similar. For example, what if I was to go into the Edit menu and go down to this Distort tool? I can now cut his height in half without affecting his width. And you can see immediately this is no longer the same shape. This is no longer the same person. He has been squished and distorted weirdly. And in fact, let's do that again. We can use this to see the definition of similarity. So I'm going to put another copy of original Ant-Man down here. And you'll notice that no matter what I do, I can't map this Ant-Man perfectly onto this one. Let's get that one in the front. I can't layer this Ant-Man perfectly onto this one using any rotation, any reflection, any translation, or any dilation. If I dilate this, I can get him back to the same height, but he's clearly not the same proportions. He's much, much wider. So these two Ant-Men are not similar. Another way that you can mess up similarity is by not changing everything in the same proportion. So for example, if I were to take just Ant-Man's body and the lower part of his head, that's not quite what I was going for. Yeah, there we go. If we were to just shrink down his body but leave his head normal, that's a little bit too small. There we go. Again, you can see pretty clearly that this is not the same shape, this is not the same person. He has a head that is way disproportionately larger than his body. And again, if I were to take original Ant-Man and move him over here, I would not be able to take this Ant-Man and dilate him up to match the other one perfectly. If I make the body the same size, the head is really, really disproportionately large. If I make the head the same size, then the body is really, really disproportionately small. So these two Ant-Men are not similar. So for similarity, you need to maintain proportionality. You need to make sure that all of your bits and pieces of your shape all grow and shrink at the same ratio. And again, ratio means multiplication. Now, Ant-Man is not only fictional, but also a very complicated shape. Technically, if Paul Rudd was to cut his hair, then he would no longer be either similar or congruent to the shape that he was before he cut his hair. So to get rid of all that complexity, we're going to take this down to the very simplest of shapes, the triangle. Okay, so here we are on the whiteboard, and we are going to find out, are these two triangles similar? Now, in an actual math class, we will have certain techniques that we'll use to determine whether two triangles are similar or not, and we'll talk about those in a moment, but using this whiteboard app, I can show you that they're similar instead of just telling you. So if I pick up this triangle here, you'll notice that it doesn't really look like it's the same shape. It doesn't really look like it's the same anything. But if I grab it and rotate it and dilate it, you can see pretty quickly that if I can get my fingers to do this properly, these are in fact, well, you get the point. These are in fact the same shape of triangle. Yeah, I can't seem to get it to stay there, but you get the point. They are indeed the same shape of triangle. Now, the question is, how do we know that when we're looking at a piece of paper and we can't necessarily dilate stuff? Well, there are two ways. Here's the first. If I know that all three angles, which I will be color coding here, if I know that all three angles from one triangle are congruent to all three angles of the other triangle, well, then I know that the two triangles are similar. They have the same angles, and in a triangle, that's enough. And in fact, because all triangles add up to 180 degrees, we actually only need two of the angles, because if these two angles are congruent and these two angles are congruent and both triangles add up to 180 degrees, then we know by default, without having to say it, that these two angles are congruent. So we call this similar by angle. If you have at least two angles in one triangle that are congruent to two angles in a second triangle, then the two triangles are similar by angle. Okay? Now notice again that this only works on triangles. It doesn't work for other more complicated shapes. For example, let's take a look at this rectangle, which also happens to be a square, and this rectangle, which is much longer and much skinnier. Actually, let's see if I can make one that the whiteboard will actually recognize as a rectangle. There we go. So I've got these two rectangles. They're clearly rectangles. Yes, we have a right angle, a right angle, a right angle, a right angle. And in the other one, we have all right angles. So in this case, we do have all of the angles being congruent, but it's pretty obvious when you look at these two that they're not the same shape. There's no way that I can take this one on the left and expand or contract it in order to perfectly overlap this other one. There's just no way to do it. So these two are not similar. So that's angle, angle. Again, quick recap. If at least two angles are congruent between two triangles, then the triangles are similar by angle, angle. So I'm going to delete this not similar stuff. And I'm going to leave this up on the screen for a moment. Now, this is an excellent time for me to talk to the class about how you are supposed to engage with these videos. At this point, you should have notes down about what I've done so far in the video, and note down any questions you have, write down any problems or any words that you don't recognize, and make sure to use those to ask me questions when I do my streaming office hours. At any time, you can pause or slow down or speed up the video so that you can go at a pace that works for you. Now, this is not the only method that we can use to find out whether two triangles are similar. Angle, angle is only one tool in our toolbox, so let's move on to the next one. So here we have two triangles that certainly look similar, but might or might not be. Remember that you can't count on your eyes or the diagram. Both can fool you. So we have no information about the angles of these triangles, so there isn't really anything we can do about that. What we can do, though, is check and make sure that all of the sides have been scaled up to the same proportion. So, for example, we've got this longest side here at the bottom, which is 10 for the smaller triangle and 25 for the larger triangle. So I want to know, what number do I have to multiply by to get from the 10 to the 25? Well, if you don't know, you can do some division and find out. 25 divided by 10 is 25 over 10, which we could simplify down into 5 over 2. Yes, I know a bunch of you reached for your calculators immediately and got 2.5, but a lot of you in class have been realizing that calculators are not perfect. They do not give you perfect answers. Fractions are almost always more accurate than decimals. So we have this 5 over 2. And if these two triangles are similar, then these should also be multiplied by the same 5 over 2, or else they're not similar. So let's find out. Over here, we have 20 divided by 8. Well, that's the same thing as, let's see, they're both divisible by 4. So we get, again, 5 over 2. How about this other one? We get 15 divided by 6. Well, they're both divisible by 3. So we get 5 over 2. So yes, these triangles are similar by side, side, side. Now wait a second. Didn't we use side, side, side for congruence? And the answer is yes. Yes, we did. And in fact, this is the same side, side, side theorem. It's just that when we had congruence, this number here, this multiplier, for the two triangles to be congruent, that multiplier has to equal 1, so that everything is the same shape and the same size. So yes, this is the same side, side, side that we used to find congruent triangles. So I'm going to erase all this information, and we're going to put some other numbers down and see what happens. Okay? So what if I have triangles that look like this? Okay, so I've got two more triangles. Again, the question is, are they similar? Now, last time I went from the small triangle to the big triangle, like that, but it doesn't have to be that way. So this time, just to demonstrate that I can, I'm going to go the other way. And I'm going to say, what do I have to multiply 36 by to get 4? Well, again, you take the second shape and divide, or you take the second length and divide it by the first length. So the multiplier would be 4 divided by 36. Well, those are both divisible by 4, which gives us 1/9. We multiply by 1/9 to get from the large triangle to the small triangle. That is the same thing as saying that the ratio is 9 going in the other direction. Notice that the ratios are reciprocals, 9/1, 1/9. That's always going to be the case. Okay, so let's take a look at this second ratio here, 27 and 3. Well, again, 3/27, they're both divisible by 3. We get 1/9 again. So far, so good. How about this last one? Well, if we take 5 divided by 40, well, both are divisible by 5, we get 1/8, which is not the same ratio as the rest. So in other words, this 36 is being multiplied by 1/9 or divided by 9, either way is correct. This one's being multiplied by 1/9, but because this length is being multiplied by something else, in this case 1/8, no, they're not similar. So with that in mind, let's look for some definitions here. We have a few definitions of the word similar, all of which are valid, but they apply in different areas. So we first determined our very, very first idea of what similarity was. And I'm going to put it in quotes because it's a really informal definition. We're going to say it's the same shape with proportional size. Now, later on, we sort of kind of upgraded this definition into same angles and proportional sides. And this gives us some really good criteria for trying to figure out whether or not two objects are similar. Finally, we have like the ultra-precise rigorous definition, which looks like this. Two shapes are similar if one can be mapped to the other, as in it can be picked up and perfectly put on top of another, using translation, reflection, rotation, and dilation. But the most important of these three definitions is this one. This is the definition that in a problem on a class test, you are most likely to find use for. It's much more likely that you're going to be using the same angles, proportional sides rule rather than using the translation, reflection, rotation, dilation rule. Because again, in most real problems, you can't pick shapes up and dilate them and rotate them to see if they're similar or not. So usually you're going to be looking at angles and sides. So with this in mind, I would like you to look at the two Khan Academy topics called Determine Similar Triangles, and there are two assignments that start with this. One says AA and one says SSS. Try those two out if you haven't yet. Watch the videos there if you haven't yet. And again, when I have my online office hours I will be happy to answer any questions you've got, and I will also go through a few problems from Khan Academy itself. Thanks for watching, and I'll see you next time.